We have already looked a little bit at the linear transformations of random variables. We now want to look at the distribution of those, not just the means, variances, and covariances. So we need to look at, in other words, multivariate transforms of random vectors. So if we first have a random vector x with some multivariate density, which we can call f subscript x, then we can consider a general transformation. We start with one-to-one transformations of x. So in other words, a g of x, and we can call that a y. Then we would like to know the density of y, where g is one-to-one. And basically what we, and this can go either way, but so I suppose I should have done this for consistency. I should have said that g of y is a function of x in some way or other, y is an h of x, so that x is some inverse transformation of y. Now, as it turns out, to do this, we need to look at the Jacobian of the transformation g. And remember, these are now multivariate, all of these. So it's not just a univariate version, but there is a multivariate version which you have seen in multivariate calculus, a multivariate version of the integral transformation mechanism to go from the density of one to another, or an integral of quantities related to one to an integral of quantities related to the other. And we just need, for now, the linear version. So suppose we have a function which is of the form linear combination of the x variable shifted, then the inverse of that is, well, you just subtract mu multiplied by p inverse. Remember, we're assuming these are one-to-one, so the inverse exists, and this is our g of y. The corresponding Jacobian is just a derivative of this function with respect to, element-wise derivative of each xi with respect to each yj, and that gives you P inverse. So that's the matrix, and then the determinant of the Jacobian becomes the determinant of P inverse. Now, we then have the general result that we know that the integral of y dy over some region in y space, so some region b, will be a corresponding integral of the over x space. The probability that x is in a region is the same as the probability of y is in a corresponding region on the other side. Now, the Jacobian of the transformation tells you that the integral over a region of these y's is the same as, or rather the integral over x in a region is the same as the integral of this particular function here. So that means that this is since that's also the integral over of the PDF of y, that tells us that these are actually the same. Again, if you need more detail, there's more detail in the multivariate statistics course or multivariate linear models course, theoretical multiple linear regression course. So what we've shown then, or what we have, is that we can get the density of y by looking at this particular density here, where we take the density of x and we simply insert the appropriate inverse matrices and the Jacobian of the inverse. So let's look at a particular case, arguably the most important case, at least in our course. And we're going to use this for other things as well. So here we're going to take x's as independent normal 0, 1s. Okay. So we then take a transformation of these x's. And here's our definition. We define that to be a multivariate, to have a multivariate normal distribution. So in other words, if you take an arbitrary linear combination of normal 0, 1s and shift them by a vector mean, then we call the resulting distribution a multivariate normal distribution, and we say that the resulting random variable has a multivariate normal distribution, or multivariate Gaussian, if you like. Now, the theorem here says that the density is given by that expression. So let's quickly prove this. The original x's are normal 0, 1. They are also independent, and they are identically distributed, which we call IID. So we then know that since they're independent, the joint density is just the product of the individual densities, since they're independent. Now, since they're identically distributed, all normal 0, 1s, we get the same expression here, except of course with different variables. And now we can pull these things together. We get 2 to the power n over 2 is what this is supposed to be in the power. So this is supposed to be 1 over 2 pi to the power n over 2, and then e to the minus summation over x's over i's xi squared over 2. Okay, nothing fancy here, but we notice this is the first time you've actually seen in this course a true multivariate normal density. It's the density of joint IID normal 0, 1s. So now we have this p function, and the inverse of that, this px plus mu, and as we said before, we know what the Jacobian is, so we know what the common density is. Now, if we write, we just define, this is wrong, this is all wrong. Well, not all wrong, but this is supposed to be a determinant of sigma. We define sigma to be pp transpose, and we see that the determinant satisfies the criterion that it's positive, so it has an inverse. And we can divide by the determinant of p, of course, because p is invertible. And the joint density then has exactly this form with some minor, we just have to notice what sigma inverse looks like, sigma being pp prime. So we have derived the density of the multivariate normal distribution using just simple linear transformations. Not too hard at all. We also know that this is a density. We know it's positive. We know it's a density because of the properties of the transformation. So the integral must be 1 because it's equal to the integral over the x space. So you'll notice that the univariate normal is a special case. If your dimension is 1, then capital sigma is just lowercase sigma squared. You also note that if the covariance is 0 between all the y's, so sigma is a diagonal matrix, then sigma inverse is just 1 over the sigma squares. And then they're independent because this whole thing falls apart into a product of densities. So that's very easy to see. Now, this is the exception, an important exception, where, in other words, if the covariance is 0, then they're independent. We said earlier, in an earlier video, that's not the general case. For the multivariate normal distribution, what we have is this theorem 5.3, that the variables are pairwise independent if and only if the covariance is 0. So that's an important conclusion. And the same thing happens to 2 collections of random variables. This is not too hard to see. You simply order them all, stick them all into one big vector. You look at the covariance matrix, and you will see that if the covariance matrix between all of them, the n plus m by n plus m matrix, if it has all the covariances between the x and the y zeros, then you have a block diagonal matrix, and again the joint density splits into 2 densities now, so that the x's and the y's become independent as blocks. And it doesn't matter now whether all the x's are dependent. That's okay. But as pairs, the x's and the y's become the vector of x is independent of the vector of y's. Now, this last theorem is something which we will use, and this is supposed to say simply xi sub I. This is supposed to be a xi, one of these guys. So, so if we have an orthonormal basis, then these xi i's are all linearly independent. They're all orthogonal, and we know that for two such linear combinations, that they will be independent also if the original x's are independent. So we can transform all these x's to new y's and get again linearly independent, statistically independent random variables. And we know their means, and in fact the variances then are just the same as the original ones, the same sigma squared as we had to begin with. So that's all I want to say on this topic, and we close this down, and I'll see you in the next video.